Analysis of three-phase, three-wire and four-wire circuits with star and delta connected loads, balanced and unbalanced. Phasor diagram of voltages and currents. So we are going to learn about three-phase system. So these three-phase voltages are generated by synchronous generator or alternator. So here we have three sinusoidal waveforms with phase difference. So this is the waveforms of three-phase system. So this is going to be your reference phase or R phase, this brown color. So we have next this Y phase. So the phase difference between R phase and Y phase is going to be 120 degrees. So there is a 120 degree phase shift, phase difference between this is R phase, this is Y phase. So after 120 degree, it starts. Next we have this third waveform is B phase. So this is 120 plus 120. So after 240 degrees, this B phase starts. So in other words, you have 120 degree, 120 degree, 120 degree between these three phase waveforms. So this is your three-phase sinusoidal waveforms. In this three-phase system, we have two type of connection. One is called star connection, another one is called delta connection. And again, here we have two type of system. One is balanced system, another one is unbalanced. So balanced means we have three-phase load. These three-phase impedances, if they are equal, then it is balanced system. Suppose if three-phase impedances are not equal, then it is going to be unbalanced load. Now, first we shall see the star connection just briefly, and then we'll see delta connection very briefly. Afterwards, we'll find out what are the currents, voltages, power in these two systems. So this is the representation of star connection. So we have, this is one phase, this is another phase, this is another phase. So these three phases are connected at a point called N. This is called a neutral point, right? So the voltage across these three phases are known as phase voltages. That is VNR, VNY, VNB. These three are called phase voltages. So this can be represented like this: VR, VY, VB, right? And we have R phase, B phase, Y phase. So this is one line, this is another line, this is another line, right? Between this neutral point and this line, these voltages are called phase voltages. So this is a phase voltage, this is a phase voltage, this is a phase voltage, right? Instead of showing VNR, we can write it as VR, VY. So this must be VB, I'm sorry. So this must be VB. And the voltage between the two lines, say R and B line, B and Y line, and between Y and R line, these voltages are known as line voltages. So between R and B, VRB, VBY, VYR, These are all called line voltages. So this is the voltage relation. Suppose if your R phase is the reference, V angle 0 volt, Vy equal to V angle minus 120 degrees. That is, this Y phase lags V phase by 120 degrees. Vb equal to V angle plus 120 degree. In other words, this B phase leads the R phase by 120 degrees, or in other words, this VB lags VR by 240 degrees. That's why we have added negative sign here. So this is your phasor diagram. So V and R, this is a phase voltage. Say if it is a reference, this is a point of rotation, this is a direction of rotation, that is anti-clockwise direction of rotation. Suppose you just with respect to this point, imagine this is rotating. Suppose this is the point of reference. So this V and R first crosses this point. After 120 degrees, this V and Y crosses this point. After 120 plus 120, after 240 degrees, this V and B will cross this point. Suppose this is the point of reference. So this is your phasor diagram. So between R phase and B phase, or in other words, this is leading. From this point of view, it is leading. From this point of view, it is lagging. Okay, so both are same, right? So between R phase and B phase, you have 120 degrees. Between R phase and Y phase, 120 degrees. Between B and Y, you have 120 degrees, right? So this end-to-end voltage, VYR, VRB, VBY, these are the line voltages. We already seen line voltages. Next type of connection we have is the so-called delta connection. So this is RYB. So we connect the windings in the form of delta. Okay. So here there is no neutral point. That means this is your phase voltage. This is your phase voltage. This is your phase voltage. This is the line. This is the line. This is the line. So your phase voltage is nothing but the line voltage. So in a delta connection, phase voltage equal to line voltage, or line voltage equal to phase voltage. Here also the same relation. VRY, R phase we take it as reference. V angle 0 degree volt, VYB, next Y phase, V angle minus 120 degree volt, next B phase, VBR equals V angle minus 240 degree volt or V angle plus 120 degrees volt. So the phasor diagram for this case is going to be like this. So VRY, so this is VYB, this is VBR. So this is going to be the phasor diagram for delta connection, and you can see the phase difference between any two phasors is going to be 120 degrees. Next we shall analyze or we shall study star connection, right? Voltages, currents and power in star connection. So as I already told, here we assume balanced system That is, impedance of three phases are equal. So the impedance of this phase, this phase, this phase are equal. Then it is called balanced system. Suppose if they are not equal, then it is going to be called unbalanced system. So this is the representation of star connection. So this is a neutral. We have R phase. This is Y phase. This is B phase. So the phase voltages are VR, Vy, Vb, right? And between R and Y we have the line voltage VRY. Between Y and B we have the line voltage VYB. Between R and B we have the line voltage VBR. So I have written here VR, Vy, Vb. These are phase voltages. VRY, VYB and VBR, these are line voltages. Since it is a balanced system, the phase voltages are equal. That is, magnitude of VR equal to magnitude of Vy equal to magnitude of Vb, that is equal to phase voltage V phase, right? So now to find the line voltage, it is going to be the vector difference of VR and Vy. Or in other words, vector sum of VR and Vy reversed. So next we shall see the phasor diagram. So this is going to be your phasor diagram. So we have VR, Vy, Vb. So 120 degrees, 120 degrees, 120 degrees. Okay. So this is the direction of rotation. Now what we are doing is just you reverse this. Just you, this Vy, you reverse. You reverse like this. So I have shown here reversal of Vy. So this dotted line, when you reverse a direction, this Vy will become minus Vy, right? So this you can, that is parallelogram law of vector addition. Probably you might have studied in your plus 2. So that means this you can move here, right? So this is VR is one phasor, minus Vy is another phasor, and this is the VRY, resultant one. So this between VR and Vb 120 degrees already. When you reverse this, it becomes minus Vy. This angle is 60 degree. Okay. So we have to use that vector algebra formula. So VRY equal to VR minus Vy. So this is a phasor subtraction. It's not ordinary subtraction because it is vector or phasor. So all these things are VRY, VR, Vy are phasors. So it is a phasor subtraction. So VRY, this VRY, you can find it as square root of VR square plus Vy square, that is VR square plus Vy square equal to 2 VR Vy cos 60. That is angle between these two phasors. So that is going to be 60 degrees, right? So VRY equal to square root of, see VR, these are all magnitude, right? Even this also magnitude. So VR, Vy, Vb all are equal to V phase. So I can write VRY equal to square root of V phase square plus V phase square plus 2 into V phase into V phase cos 60. VRY equal to square root of V phase square plus V phase square. Here V phase into V phase. So you get plus 2 V phase square cos 60 degree. Okay. Next we have VRY equal to square root of 2V phase square plus 2V phase square cos 60 value is 1 by 2. So this 2 getting cancelled. VRY equal to square root of 2V phase square plus V phase square. VRY equal to square root of 2 plus 1, 3 V phase square. So VRY equal to, I separate this into two parts. VRY equal to square root of 3 multiplied by square root of V phase square. So this will remove the square. So VRY equal to root 3 V phase. So this is for one phase, but we are assuming a balanced system. That means the line voltages VRY equal to VYB equal to VBR equal to one line voltage, right? So I can write in terms of line voltage, so VL equal to root 3 V phase. In other words, in a star connected, in a balanced star connected system, line voltage equals root 3 times the phase voltage, right? What about currents? What about currents? If you have, I will again show you, if you can recall, just for your convenience, I will show you. So here, the current flowing through this phase winding, it is called a phase current, whereas the current flowing through these lines, through line, it is called line current. But in this star connected system, the same current, that is the current flowing through this phase winding, is the same current flows through the line. So here also like this, here also like this. So based upon this, in a star connected system, we can write the line currents equal to phase current. That means, but this is a balanced system, so all the three currents are equal. IR equal to IY equal to IB equal to I phase. So these are all line currents. So IL equal to I phase in star connected three-phase system or star three-phase system. Next we shall find expressions for power. So power, total active power capital P equal to 3 into V phase into I phase cos phi. So here this is the power of one phase, V phase, I phase cos phi, that is current multiplied by voltage multiplied by the angle between current and voltage. So it is nothing but single phase power. Power in a AC circuit, single phase AC circuit, VI cos phi. Same formula, V phase, I phase cos phi. Since it is a three phase, we are multiplying by 3. So active power P equal to 3 into V phase, I phase cos phi. So P equal to this 3 I write root 3 into root 3 V phase, I phase cos phi. So root 3 V phase is VL. So P equal to root 3 I phase is also IL cos phi. So this is the active power in star system or in star connection. So phi is the phase angle between the phase voltage and the phase current. Similarly, Q is the reactive power. It is going to be root 3 VL IL sin phi. Right? Next we have S. S is the apparent power, which is nothing but square root of P square plus Q square. So S is equal to, substitute P and Q values here. So root 3 VLIL cos phi the whole square plus root 3 VLIL sin phi the whole square. S equal to, just to square this term, 3 square root of 3. So 3 VL square IL square cos square phi plus 3 VL square IL square sin square phi. So 3 VL square IL square take outside. So you get S equal to square root of 3 VL square IL square into cos square phi plus sin square phi. So cos square phi plus sin square phi is nothing but 1, right? So you get S equal to square root of 3 VL square IL square. So you take square root, you get root 3, this will become VL, this will become IL. So apparent power is equal to root 3 VL IL. So these are all the voltages, currents, how phase voltage is related with the current how phase voltage is related to line voltage, how phase current and line currents are related, and expressions for power, active power, reactive power, apparent power. These things we have learnt in this session.